doesn't have to be something that's implemented in Haskell. It's everything
Right. So, yeah, so someone was talking to me about a mental model. Yeah. Sorry?
To me, just X and D doesn't really...
No, just was actually back in C, was in Hask. And this was in the weird partial function world.
Before you erase that, you said that that's a singleton of X, and then it goes down to 17. Is that actually the singleton?
No, this was singleton.
17?
X to list X.
That's 17.
This was the unit. This was the co-unit.
Right. The co-unit, does it really return 17, or the singleton set includes 17?
17. This goes from a monoid, which is natural number 0 plus. It takes the list monoid with append, and this is a unit. This is a monoid. A list M with this unit and this multiplication. It has no idea what multiplication in M looks like. It doesn't know. 3, 3, 2, 8, 1 is a perfectly good element. But I can send it into something living in this monoid. Back in M, I can send it to 17 itself, the number.
But didn't we start off with the X? Oh, that's
no, this is two different. This is the unit.
Two different things.
This is living in set. This is living in a monoid. So given a set, I can go to the set list X by sending any
X. That's C right there. The set is C.
Yeah, this was set.
Is C.
Set, which was C, and monoid, which was D.
17 is not an element of set. 17 is just a number. It's a natural number.
17 was an element of the monoid. Yeah.
But doesn't like the co-unit?
This was an example of the co-unit. This is the co-unit. The co-unit goes from list M, empty list append, to M E star.
Yeah, but why is it 17 as opposed to a member of a set?
M was
C is a set, D is a monoid, but 17 is just a number. It's not a set.
It's an element of this monoid.
That's why he's saying that that's just an example. He's not saying the whole thing's an example. He's saying that that's an example.
A different example.
No. Well, it's kind of like an instance of transformation.
Okay, I'm giving a map of monoids. Yeah, a map of monoids from this guy to this guy. A map of monoids means for every... Okay, he's talking. So, any other questions? Yeah.
With co-unit, on the left side we should have monoid. So on the second line we have arrow goes from list to monoid, but I thought that it should go from monoid to list.
No, I said it would go from LRD to D. So the D is the one on the right, and it's remaining undecorated. And on the left, we get all this extra stuff. So we get M
On the right.
and all this stuff on the left. Okay, so where do monads come in? So monads, so let C be a category. Oh, does anyone care about Galois connections?
Oh yeah.
Yes.
Okay. Yeah.
I have a quick question. Maybe you can answer with a yes or no, if there's no interest in further. A lot of this is making me think of like translating from one language to another and then back to the first.
Yeah.
Has there been any work on applying category theory in any way to language translation?
I wish. I always thought that's what it was for. But no one seems to do that, so I don't understand why not, but maybe it's hard for some reason. I don't know.
The words are your objects of your category, and then the arrows are your like the grammatical structure, like the syntax.
Oh wait, did you say? Wait, what did you say? Oh, I thought you meant languages like programming languages.
No, I mean
like DSLs and
too, but like I mean any language, any form of like communication, really.
Well, because a lot of like natural language is really not good.
I know, which is why it seems like you'd be like, and there's a lot of, I know there's a lot of people that work on natural language processing. I wonder if they ever.
But it's never going to satisfy all the things. It's like going to fail. Like it's like dirty data. Like natural language is dirty data. Yeah. And nothing's like this is. This just works too well to. I mean, I don't know. It doesn't apply.
You mess it up by applying reality.
Yeah, exactly. It's a way of thinking, and maybe it's the right way of thinking for what you want, but it's probably not going to work out of the box. right? Okay, so Galois connections. If C and D are posets.
What is it that everyone got so excited about? Some of us don't know.
Okay,
Can you just write
then
what you're talking about?
yeah, then a Galois connection is an adjoint pair, a pair of adjoint functors. So you don't know what it is, but I've actually just completely defined it. C, D, L, R. So let's unwrap what this means
Oh, okay.
instead of telling you what an instead of telling you what a Galois connection is. I've already told you what it is because posets are just categories where every morphism set, Hom set, is either empty or has one element. So these are perfectly good categories. And to say I have an adjunction, I've defined it already. It's like a functor one way, a functor the other way, and this like isomorphism, Hom LCD is isomorphic to Hom CRD on that board over there. And that's what it says. But if you translate what that means, it says for all C and C and D, these are objects in your post set. L of C is less than D if and only if C is less than or equal to R of D. If you have that set up, you have an adjunction between the post sets, and that's what a Galois connection is. So I could give you an example, like kind of a nice example.
Yes,
Okay.
Like what's the implications of
Oh, I don't know. Power. Do you like power sets? Did you say?
it? Yeah, but yeah.
Okay, great. So say you have two sets, A and B, and you have a function between them, f. You have two data types, I guess, right? A and B have a function. Then you can take the power set of A. Do you guys know what that is? The set of subsets of A. So if that's A, then the power ABC. Oh, I already wrote this, in fact. The power set is empty set, A, B, C, AB, AC, BC, ABC. And it happens to be a post set. But I'm just looking at it as a set. A post set has an underlying set. That's a functor from post sets to sets. No, there's a functor from post sets to sets.
Therefore, it is a subset by definition.
No, I was just like doing.
Faithful.
I was just like throwing in like stuff for no reason. Okay, so no, I do want these to be post sets. Right, sorry. So there's a functor from set to post set. And that's the power set. Yeah.
That's another free thing?
I think so. I don't know. Maybe not, actually. So, but that's not what I'm going to use here. That's just a fact. This is a post set. And there's a function, there's a post set map. In other words, a monotone function from power set of A to power set B. What would you do?
What's a monotone function again?
Meaning, if something's less over here,
Right.
it becomes less when you apply the function. So suppose you had a subset of A. You're trying to get a subset of B, and you're given F. What would you do?
Map them all first and then
Yeah, you'd have this subset of A. You'd map them all by F. You would get a bunch of things in B. You might get repetition, but you're not allowed to for a subset, so just throw away all the repetition. That's a subset of B. That's called the image of F. You have a subset of A, you take its image. There's a map back that takes a subset of B and gives you a subset of A. How? So you have a map from A to B, a function, and now you have a subset of B. What subset of A should you choose? Pre-image. Yep. F inverse, it's called. So F inverse, so suppose U is a subset of B, then F inverse of U is going to be the set of A in A such that F of A is in U.
how do we know that F is in
F is not invertible. F inverse is the name I'm going to give that maybe I'll call F upper star instead, so he doesn't confuse anything.
So what do we do if we get an element in, or a subset in B that's not mapped to by?
Then I'll get the empty set. I just take all the A's that happen to go into it. And if that's empty, fine. If it's everything, fine.
So this whole thing is in set, or what's A and B?
A and B are sets. Oops. In set. And when I apply power set, I get a poset, the set of all subsets of A, ordered by inclusion.
What do you mean ordered by inclusion?
Meaning that if I have two different subsets and I want to know if one's less than the other or not, I ask if it's a subset or not. So this is a poset. It kind of looks like this. Whatever. And IMF, is it monotone? Meaning, if something's a subset in A, and I apply IM, is it a subset in B? If I have two elements of A, if I have two subsets of this thing, U inside of V, and I apply image of F to U, and I apply image of F to V, will the image of F of U be a subset of the image of F of V?
What's it mean to do the image of F again?
It means take all the things in U, look at where they went in B. So suppose you have this function. And if I take any subset here, I get a subset there. It's the image.
Oh, of just whatever you do.
Yep. And if I have any subset here, I can take the pre-image, and that's going to be these two. So these are both.
Two of those would go to the empty set because they're not mapped anything. On the right there.
If I took these two, the pre-image of this, I'd get the empty set. Yep. Okay, so these are both monotone, and they form what's called a Galois connection. Because image of F of U is a subset of V if and only if U is a subset of the pre-image of V. That's what it means to be a Galois connection. Yeah, it's an adjunction between posets. And all I'm saying is that given a function is set, you get an adjunction. Yeah.
Is this more general than just the poset function, or is it anything that has like initial and terminal, and you're able to map everything over?
The notion of adjunction works between any two categories. You can ask whether two functors are adjoint. And in particular, for any two posets, you can ask whether one monotone map and another monotone map are adjoint. And I'm giving you like a whole supply of them. For any function, you get one of these guys. I could give you another Galois connection if, yeah.
Is U and D, U is an element of D still, and D is an element of A?
What's U and V now? What are you talking about?
U is in A, and V is in B. Okay, so
How does that evaluate though? You're saying the image of F.
applied to U. Image of F is a way of taking things in here and getting something in here. So this could be written F of U.
Okay. Okay, got it.
So is this only true if you do a round trip?
Is what true?
Well,
This is this thing here, this if and only if, is exactly the isomorphism I need for my adjunction. It's exactly the Galois connection condition.
How is F star monotone?
Okay,
For example, if you have like a subset that's
if I have one subset and then a bigger,
that didn't get mapped from A.
yeah. Say I have a subset in here and then a bigger one.
Yes.
Whether it got mapped or not. Then if I look at all the guys that mapped into the smaller one versus all the guys that mapped into the bigger one, there'd be at least as many in this bigger one than as in the smaller one, right? Like if I take F inverse, you're asking if V1 is contained in V2 over here.
Oh, strict subsets.
No, this kind of subset, non-strict.
Why didn't we end up with an A+1 when we came back from the things that didn't map? Remember before, like we had to have a sort of a bucket for the stuff.
This guy, that was for partial function. These are like posets.
Just a different thing.
It's all subsets. Yeah, it's just a different thing.
Isn't the
Yeah.
point we already have the
There's so much going on here. I feel like everyone's brain is full. But
Yeah, but keep going, because this could lead into monoids somehow.
so we end at 5:30, which is 45 more minutes. And I guess I should talk about monads before we go. So what I've just said, though, is that Galois connections, I don't have to tell you what they are. They're just, I tell you that they are adjoints, just happen to be between posets. So anyone who's studying Galois connections is actually studying adjunctions. They're just doing it in a limited subset of cat. They're working in poset, which is a subcategory of cat. This idea makes sense more generally, and is useful for doing currying, like for creating monads, all sorts of things. Adjunctions are more useful they come up more often than just Galois connections. Okay, so suppose, a monad, let C be a category. A monad on C is, or consists of, one, a functor M taking C to C. Two, a natural transformation from identity of C to M. And three, a natural transformation from M, circle M, to M. This one's called eta, and this one's called mu for multiply. This is going to be the join, and this is going to be the return.
Haskell, is C going to be Hask?
Hask.
Or is C
is going to be Hask. Satisfy such that some stuff. Want me to write it? You care about the laws? You want the laws? Okay. Such that if you have M and you go to MM by unit, and then you go back down to M, that's the identity. I don't think you're going to like this because I'm doing it too. I'm writing in like category theory. These two diagrams commute. Meaning, so what is that? And more, so one more thing. MMM maps to MM, maps to M, maps to MM in a different way, maps to M. Unit, or multiply, multiply, M multiply, multiply M.
This is not
See?
M. These are not product sets.
This is M of M of M.
M of M. Oh,
Yep.
Okay, because it's a monad. All right.
So what is this? Let's talk about list. So list is a monad.
Okay.
What this says is list goes from set to set. There is a singleton, like sing. I don't know what you call it, sing, or return, from sing taking X to list X. For any X, singleton X. That's natural in X, meaning if I have a map from X to Y and I get a map from list X to list Y, and like if I take the singleton on X and look at it and then map, it'll be the same thing as mapping and then take the singleton. And I also get a join or append. So append is a kind of join, so I'll call it append. From list of X to list of X. So the elements of this, as an example, are things like a list of lists, a list of lists. And this append takes a list of lists and returns a list by appending them all together. It's flatten. It's a flatten. Flatten. And this says, if I take a list, and I think of it as a list of lists by taking a singleton, just one big singleton. So I take ABC, ABB, and I think of it as a singleton list, and then I flatten it, I get back where I started. And if I think of it as a list of singletons, this one says, if I think of it as a list of singletons and I flatten, I get back where I started. That's what these commuting means to me. And this one means, if I take a list of lists, and I flatten the interior lists, I'll get a list of lists, and I flatten again. It's the same thing as flatten the exterior lists, and then flattening it again. That's what this thing says.
So why did we need that second square?
This one?
Like, that doesn't, we don't get that from the first?
No. Why not? What's an applicative that, no, that doesn't make sense.
Are you trying to prove like associativity of the flattened operation?
Yeah.
He's asking why associativity doesn't come just from the singleton laws. This is just laws about singletons. Yeah. So I don't know off the top of my head an example of one that doesn't satisfy this, but you certainly don't get it for free.
I have a question.
Yeah.
So these diagrams you drew, they're not extra information, they're just another way of representing.
No, these are such that. These are properties such that A and B.
So are there, we could find a natural transformation from M to M, but don't fall.
Oh, yeah, definitely. They don't obey these laws. So for an example of a natural transformation, you could send everything to the empty list, I think. Well, I don't know. Okay, I'll take a list of lists and I'll return the empty list. That is going to be that's going to be a natural transformation, but it's certainly not going to obey very much. It's not. I mean, let's see. Right, it's not going to obey this. If I take my list, I turn to a list of lists, and I return the empty list. It's not the same as identity. These equal signs mean the identity. Yeah.
The second one is to prove associativity. I think someone said that, and I think that makes a lot of sense for the first time that I kind of got that. Is that right? Is that the reason why that second one exists, to prove associativity?
Flatten twice.
The ways, the sequence of which you flatten doesn't matter.
Right. Okay, right. So this is what a monad is. So list is a monad, maybe is a monad. Do you want to see these monads? So maybe C. So maybe take set to set. I get a map just from X to maybe X. And I don't know what this one is called, but it's the bind. I mean, it's the join. If I have a maybe X, I get a maybe X. What?
Like flatten up identity.
Flatten up the nothings. Flatten up the nothings? I don't know. If I have a maybe X or I don't. If I don't, I get nothing.
Right.
If I have a maybe X, I get the maybe X.
You might have like just nothing though, which is,
I get nothing.
nothing.
Yep. And the laws, what do they say? I mean, they might not be as interesting in this case, but I guess if you have a maybe and you go to a maybe, and you go back down to same, like if you take your maybe X, you look at it as a maybe X by just. This is the just. And then you flatten flatten the nothings to nothing. You get the identity on that maybe. Or for state. State's kind of, so what does state say? So state A, taking set to set, I get a map from X to X times A to the A. And this is, you're thinking of it as identity. That's what you told me before you were thinking of it as. Given an X, you need a function that takes an A and gives you an X times an A. And it feels a lot like identity.
That's the unit and the identity is what you're saying?
That's the return. of this monad, the state monad.
Which is the unit, right?
It's the unit. And the other one, the flattened thing, takes you from, this is kind of hard to look at, but x times a to the a times a to the a, and gives you an x times a to the a. So suppose you had a way of taking an a and giving yourself both a new a and a function that takes an a and gives you both a new a and an x. Then, given an a, you could get an a and a function from a to a times x and evaluate and get your x times a. And that evaluate was the co-return, if you remember. So, yeah. Okay. So this is the join and the unit for that monad. And the point is that every adjunction has a monad, and every monad has, and various adjunctions might go to the same monad. But, so how do you get a monad from an adjunction? Right. So you have an adjunction from C to D. You have an L, and you have an R.
Can you erase the F and the stuff at the bottom?
Yep. And you have this unit and this co-unit. So you have the unit taking identity on C to RL, and you have the co-unit taking LR to identity on D. If you remember, we got both of these from that universal property by looking at identity and stuff. So the monad, the associated monad on C is RL. M equals RL is the monad. And how it works is I need a map from identity to RL. Like if we look at what I said I needed, is it still there? No. Oh yeah, it does. Yeah. I need a natural transformation from identity on C to M. My M is RL. So I need a map from identity to RL. And that's just eta. So that's the return. And the other one is a map from RL to RL. That's the MM to M. And what it does is it takes these two things and crushes them to an identity. So it just goes from this to R identity L, which is equal to RL, using co-unit. So it crushes these middle two guys. That's where that evaluation was taking place over there, was that for the state monad, the adjunction was currying. And one of the two sides of that was evaluation. And that's why we evaluated. Like, none of this stuff, I didn't invent this. This came to us from the idea that there's an adjunction between times A and power A. And once you know that, you get this state monad. It's just the thing you get. You call it state, but it's known mathematically before you know that it's useful.
Why did you say times A and power A?
The adjunction I was talking about was the one that takes a set and multiplies by A.
And that's times A?
I called that times A.
Oh, got it.
And then this one was takes a set and raises it to the A power.
Power A. Okay. So it's not like the power set.
No, sorry.
Ah,
Yeah,
okay.
yeah. So that's how the monad comes to you. It comes to you from an adjunction. But the point is, if you had Hask or some other category you really care about, if I just had some other category, kind of like a mental model, and I had an adjunct, like this is the wide world, right? Where people are entering things and someone's setting off like various processes in the real world. And you had a functor, one way and the other way. You don't have to know what D is to get a monad on Hask. Like this could be set, and this could be par. This is like a wider world than set, right? It's got stuff you don't like. And yet, when you go around, you get a monad that lives only on set. It takes a set and pluses 1 to it. And so you don't, it's like set's interpretation of par.
So that's how you handle I/O, because I/O is scary and
Yeah,
bad.
right. This is the wide world where inputs and outputs are happening, or state is happening, or whatever is going on. And this is just Hask. And although we pass through D, Hask doesn't have to know about it. It just has to know LR, like how do I associate a new data type to a data type? How do I associate some kind of return and some kind of bind or join? And that's kind of the relationship. There's this other category that's bigger, usually.
What about the epsilon where you actually get back what's in D? Because you get the ID of D. LR goes to ID of D. The epsilon.
That says that if you do,
That's how you extract the.
oh, well, you don't have to know about that. So that's the thing is when you have par, the Haskell programmer or whatever is not working here. They're working only here.
But what is it ID of D?
That's over here.
Right.
This is a category you don't care about. So what this does is internalizes D as best can. It internalizes D and L and R into C. It just, all of this, so, okay, this is happening in C,
Yep, that's easy.
and this is happening in D.
Right.
But a monad is happening R,
Oh, the
epsilon
ijoins
L.
end up epsilon because the co-unit is in the epsilon is in D because that's the
Yeah.
ijoin. But the point is, you then use that to create the monad, and then
Only
the
on
monad
C.
only knows about C at that point.
Yep. So every monad you have, there's some other category. In fact, the Kleisli category always works, and something called the Eilenberg-Moore category always works. But it could be any category. If you had an adjunction, any monad you have came from an adjunction. You just might not be thinking about what that other category is. But it's out there somewhere. It's some wider world that is beyond your programming language, possibly, but that you are interpreting within your programming language using, like the translations back and forth. You're interpreting all of that internally.
What's the name of that other one? Is the Kleisli and the Eisenberg what?
Eilenberg-Moore. So these are ways of getting out of a monad, like folding up a list. Do you want me to talk about, I was planning to talk about that. Is that a good thing to talk about next?
About what?
Eilenberg-Moore category? I haven't heard of it. Okay, it's a way of getting out of a monad. That's what I would say. It's like a category theoretically nice way of getting out of a monad. So suppose you have a monad. You're asking for clarification?
Yeah.
Okay, I'll just say. So suppose,
And does that relate to comonads or is that different?
oh, okay, so a comonad. Let me quickly say that. Given an adjunction, you also get a comonad, associated comonad. And that is, I'll call it N. It's going to be LR. It's going to go R and then L on, it's going to be a comonad on D. So if on this setup, if L is left and R is right, your comonad is going to live on the category you know nothing about. So it's only if Hask is kind of on the right that you're going to get your comonads. But anyway, so it's LR with epsilon and L eta R. And I know that's not very easy to parse, but it's just the opposite thing. You just do the other one. So let's not talk about that,
Well, but
just so we can.
comonads are really important, you know, so
Okay, so they may be more important than Eilenberg-Moore category.
I don't know.
We don't know what that is. It's a way of getting out of a monad.
Let's do that.
Okay.
Yeah, that sounds good.
Okay. So suppose C is a category. So you have this category, and you have and M with eta and mu. Oh, I should talk about the Kleisli category too. I'll talk about that first. Is a monad.
We're talking about Kleisli.
Yeah. The Kleisli category for this data is the objects of Kleisli C are the objects of C. So nothing's changed there.
Hey, where's mu, by the way? You just
Mu.
have mu over there, but you didn't have a diagram over there.
Oops.
Oh, join.
Join.
Okay, sorry.
Mu is join. I erased it
Well,
already.
that's it. Actually, it's that one down the bottom left. It's our LLR. Isn't it over there?
Oops, yeah, this is mu. It's the join. So suppose you have a monad with a return and a join. I'm going to tell you how to get bind. The Kleisli category is where bind comes from. So it says the objects of the Kleisli category are just the objects of C, Hask. So you have the same objects, but you have a different kind of morphism. Hom in the Kleisli category from one object to another is Hom in the old category, C, from C to the monad on D. From C to monad D. So that's kind of weird. What are the identities? I need a map from C to monad C as my identity from C to C. And that's going to be return. And what are the compositions? If I have C to monad D, and I have D to monad E, how am I going to get C to monad E? Well, I do C to monad D. I apply the functor to get from MD to MME, and then I join out of it to get to ME. And that's called the Kleisli category. So what this says, so let me just write this type theoretically. So it says if I have C to MD, for any object C, D, and E in Hask, C to MD, I'm writing it in your usual notation, like arrowed notation. Okay, I'm changing my notation to what I think yours is. C to MD, D to ME goes to C to ME. And I could drop this, right? That's what this is saying. If I have a map from C to MD, the composition law, this is the composition in Kleisli. I take a C to MD, a D to ME, and get a C to ME. And if you think what happens if C is unit type, then a function from unit to MD is the same thing as an element of MD, right? A function from unit type to anything is just a term of that type. So this would become, if C equals unit, this becomes MD, this becomes D to ME, and this becomes ME. And there's bind. So bind is kind of a special case of the composition. Does this look like bind? Okay. This is a special case of the composition law in the Kleisli category that kind of works no matter what C is.
And you're putting
Yeah.
void not identity into C.
Unit.
Unit.
What?
Unit?
Unit type. It's got like one element that's like an empty parenthesis.
Haskell, right?
Void. Unit. Unit? It's called unit. Okay.
When you're lifting the D to ME, are you lifting it?
What D to ME? That's not a lift. That's a function in
No,
Haskell.
so when you're applying the functor to get the MD.
Oh, I apply D. The functor. I get MD to MME, right?
So when that's happening, are you using like the neutral value of the functor?
A functor always takes an object to an object, so it takes D to MD, and takes any morphism and gives you a morphism. So this is the F map.
So I guess I'm just saying it's not adding any new information to the system. It's a neutral add, so that it can be neutral. This is kind of a big deal. People talk about join as being this.
It might be. I don't know how to parse the question. I would say it's not computation. I'm guessing, unless you think of if I have a map from X to Y and I get a map from list X to list Y by map. I don't know if you think of that as computation or not, but
You get one of them for free, right? Like if you have return, you
yeah.
implement bind, you get join. If you have return, you have join, you get bind, right?
Okay, so that's the Kleisli category. And there, in fact, is an adjunction from C to the Kleisli category of this monad. I probably should have called this Kleisli of M instead of Kleisli of C.
Wait, it should be the Kleisli of M up there?
I would think it's better notation, but I was just fast. I was just being fast. So there's an adjunction between C and the Kleisli category. I'm not going to tell you what it is, but like you can get, I told you given any adjunction, you can get a monad. Given any monad, you get an adjunction. And there's some kind of round tripping, but not a full round tripping there.
Because the point is, like, you're not really, because of the adjunction, you're not really aware of the fact that you're in the Kleisli. You're just doing bind and it all works out because you're still kind of living in the C.
I guess so. Okay, so there's another category you can associate to a monad, and that's the Eilenberg-Moore category. So given C and this M with the unit and the join, So to a category theorist, the unit and the join, or at least to me, unit and join is more basic than bind for me. But I think just as an program language idiom, it's less useful. But mathematically, it's kind of less data. So I usually think about monad as these three things: m, the functor m, the unit, and the join, the join and the return. So you can associate to this the Kleisli category as we did. There's also the Eilenberg-Moore category. So Eilenberg was one of the two founders of category theory, and Moore, I think, is a topologist. So given this, we are able to get, actually I'm not sure who Moore is, sorry Moore. We are able to get an Eilenberg-Moore category. And how does it work? The objects, well, there's a lot to say here. These are ways of getting out of, are called M algebras. So what is an M algebra? It consists of an object, C and C, and a map, a morphism, MC to C, such that if you have C and you return an MC and then you apply your map, you get back out of the monad. So think of M's the monad. It's a way of taking something in the monad and getting out, such that if you return into the monad and then get out, you're back where you started from. And such that if you have MC, there's two things you could do. You could join to get an MC, so you could have a list of lists. You could either flatten it using mu and then get out using H, or you could get out, like take your list of lists and get out on the internal lists to get an MC, and now you just have a list of C's, and then you get out again. That those would be the same thing. So it's a way of getting out of a monad in a way that works well with the unit and with the join of the monad.
What is it? What monad?
So let's say M is list. Then in order for you to have an algebra, you're going to need a monoid. The only algebras on list, the only list algebras are the monoids. It's going to be an object, say the natural numbers, and a way of taking a list of naturals and giving yourself a natural, such that if you take the singleton list, you get back your natural numbers. And if you take the list of lists and you multiply out your list into naturals, and then you multiply that out, this is going to be the associativity law, and this is going to be the unitality law of your monoid.
Terminology, what's the OB mean?
The objects of the Eilenberg-Moore category are M algebras. And the morphisms are morphisms of M algebras, but you probably don't care that much.
Monad algebras or just M algebras?
Monad algebras.
Okay, so what's an F algebra? Is that just a functor?
What's an F algebra? So, right. So the Eilenberg-Moore category takes any monad and gives you back algebras on that thing. These are guys from MC to C. But this idea of maps from MC to C actually makes sense if M is any functor. It's just that if it's any functor, you wouldn't know how to interpret either of these two diagrams. So monad algebras are more restricted. They're like what fold is. I think it might be, I think it's really actually good. Fold is to monad algebras as R fold is to F algebras. Is that good? Okay. It's like I'm venturing lightly into, okay.
So you're able to talk about comonads, or what?
I wasn't planning to. Well, but I can. We have like 15 minutes.
What else do you got to cover?
I was going to tell you about initial algebras, like F algebras and final co-algebras.
Oh, that's good. Yeah, let's do that.
All right. Wow, I use a lot of chalk.
I was Yeah.
So monads include three things. They include a functor from C to C, a unit, and a join. But if I didn't have the unit and join, I just have a functor, I can still talk about algebras. They're just a little floppier. They don't have this rules about return and join because there is no return and join. So this is called an endofunctor because it goes from C to C. And that's where, if you're living in Haskell, you live in like functor means endofunctor. So if you're ever looking in category theory world about functors, remember that when you think about functors, you probably are thinking about functors from C to C, right? That's a takeaway. So that's called an endofunctor, and you can talk about algebras. So an algebra, an M algebra,
Which is the same M algebra over there.
is a choice of sort of a C and C, and 2, a function or a morphism in C from MC to C. And it's not quite the same as that one because that one required more things. This one doesn't have a unit, doesn't have a join, and therefore doesn't require them. So every M algebra in that sense, if you forget the monad and just think of the endofunctor, it's a forgetful functor. If I take my monad, just think of it as a functor, I take my algebra, I'll get an algebra. But some algebras here may not be algebras there because they might not satisfy the extra things. A morphism of algebras, of M algebras. Oh, I'm giving you a category now. I didn't even say that. A morphism of M algebras is a morphism, or consists of a morphism. So if I have like C and H, and I have D and C prime and H prime, that's an algebra and that's an algebra in this notation. Oh, H. Then a morphism is a map C to C prime such that I have M C, I have M C prime, that's M of F, I have H, I have H prime, I have C and C prime, and this should commute.
What's the value of an M algebra then?
Right, what is it?
The rules, but like what do you use it for?
Yeah, so let's talk about an M algebra. So suppose you have, by the way, an initial object in this category, meaning one that maps uniquely to everything else, will give you lots of interesting data types called, what are they called? Well, initial algebras, but I feel like they're kind of like
Algebraic data type?
algebraic data types. So what's an example? Say you have set, and the functor, so fix a set A. Fix it for the discussion. And I'm going to take a set X and send it to A times X plus 1. So take any set and just send it to this weird set. Maybe A times X.
Just like a label set plus something else.
Plus some A, plus a nothing. Then an algebra for this M is a set, say X, and a function H taking A times X plus 1 to X. So in other words, to give such a function, I'd need to give where the 1 goes, and I need to give for any AX a new X. If you do that, you have an algebra. The initial algebra for this turns out to be list A. List A together with the map list A times A plus 1 to list. Can anyone think of the map from A times list A plus 1 to list A? The function. So I either have an A and a list A, or I have one. I have something. I have like a unit type, and I'm supposed to get a list A out of that.
The empty list of the...
And the cons or whatever, right? Yeah. So it's cons this and empty list there. That's the initial algebra for this, meaning for any other x, where you know how to take an A and an x and give an x, you know how to get an x from nothing, you will get a map from list A to x that works correctly in this sense. Like x knows how to take an A and an x and gives you an x. List A knows how to take an A and a list A and give you a list A. And if you kind of do it in either order, you get the same answer. So suppose I have this data.
What's that notation mean? X comma h. So given an x.
This means to give an M algebra, I give you a C in OBC and I give you a morphism. I'm pairing them up.
That's the C and the morphism.
Yeah, yeah, that's the H. So suppose someone gave you a type. They gave you a way to get it, take an A and an element of that type and get that element, and they gave you just a free element of that type.
So like,
how would you get a map from list A to that type?
is that head? Sort of like?
So they give you these. Remember, a map from A times x plus 1 to x, you can think of it as two maps. By the universal property here, it's actually just a map A times x to x and a map 1 to x. So it's just a unit type to x, so it's just an element of x, and a way of scalar multiplying somehow, A times x to x. They give you this data, and for some reason I'm telling you that there's a unique map from list A to x that satisfies this property. Which one would you choose? Let's call this guy.
Is that church encoding or something like that? Or?
I don't think so.
Okay, no,
This is fold. Fold left. Fold right. I don't know how to write it. Fold R. Why? I'm going to take empty list to this guy, and then I'm just going to take an A. I'm going to have a list of A's. I'm just going to take my A and do whatever I said I was going to do. Just keep popping it onto that empty list thing. And fold R is going to be the exact thing that says if I take a list, if I take an A and a list A, and I cons, and then I fold, that's the same thing as somehow, and then that's the same thing as keeping my element aside, folding, and then hitting it again with that last. And then, anyway, it works. It just check it in. So a terminal co-algebra. A co-algebra is exactly dual of this. Dual means kind of make all the arrows go backwards. So it's a co-algebra is a choice of an A, what did I call it? An X in OBC, and a map from, say, H taking X to MX.
If that's ADTs, is that basically a final tag list?
Which one's ADT?
The one you're about to write now, is that final tag list?
What's this for? What's the initial algebra for?
If that's a final algebra.
You're asking what's the final coalgebra for this functor?
Actually, just move on. Sorry.
Okay, so here's a functor. So I can ask what
algebra, which basically is ADTs.
ADT. It's list with fold. Okay, so given a functor, given an endofunctor, I'm able to ask what is the initial algebra and what is the final coalgebra. And for this particular functor that takes x and returns A times x plus 1, we found that the initial algebra was list A. And the reason it's initial, what some people call the catamorphism, I think, is fold R. Like lists and fold R come to you from category theory in terms of this category of M algebras as kind of list, as kind of the initial one. And the final coalgebra is going to be stream x. And what is stream x? What I mean by that is possibly finite streams, possibly infinite streams. And I need to give you a map from stream x to, stream A. From stream A to A times stream A plus 1. So given a stream A, how do I unfold it, if that's the right term, and either give a 1 or give an A and a stream A? Well, I have a stream A. It's possibly finite, so it could even be empty. If it's empty, return 1. If it's not empty, return its head and then the tail stream. And this is a final coalgebra, meaning that if you have any way of taking x and getting A times x plus 1, meaning for any x, you either get nothing or you get an A and an x, then you can get a stream out of it. So I could tell you how to go from list A to stream A via all this stuff if you want. Like, what's the map from list A to stream A? It comes to you from this initial terminal stuff. It's kind of a weird derivation, but so I need a map from list A to stream A. So to get a list A to anything, I need to give a map from stream A. I'm going to call it ST. From stream A times A plus 1 to stream A. So it suffices to have this, right? Do you see why? To give a map from, list is the initial algebra, which means if anything else is an algebra, there's a unique map from list to that algebra. So if I could prove that stream A was an algebra for this endofunctor, then I would get a unique map. I would have one. So all I need to show is that stream A is an algebra for this endofunctor. I just need to produce any map like this. Agreed? OK, so how do I produce this map? To give a map to stream A, since it's the final coalgebra, it's enough to give a map from A times stream A plus 1 times A plus 1 to A times stream A plus 1. Because to show that a map to the final coalgebra is just to give a coalgebra structure on this. So all I have to do is give you a map from A times stream A plus 1 to A times stream A plus 1. I don't know.
So the keynote's going to start pretty quickly.
Oh, at 5:30 or?
Yeah, 5:30.
Oh, I thought we were ending at 5:30.
Yeah, and then it's 5:30. So I was told
Oh.
5:30 sharp is.
5:30 sharp.
Okay. So.
Okay. Anyway, this is easy. It's actually f of h, where f is m. And that's this. The end.